Is numerical number 3.6. A negligible small current is passed through a wire of length 15 meter and uniform cross section of 6 into 10 raised to minus 7 meter. The resistance is 5 ohm. Find the resistivity. You just have to write the values in the equation. The equation for resistance, as you know, it is R is equal to rho L upon A. So rho is equal to AR upon L. Value of A is given. Value of A is 6 into 10 raised to minus 7, multiply by the resistance, that is 5 divided by 15. So the answer you will get, that is in ohm meter. Okay. Now example number 3.7. A silver wire has a resistance of 2.1 ohm at 27.5 degrees Celsius. So here this is your initial temperature and this is the initial resistance, say R1, and this is say temperature T1, and resistance becomes 2.7, that is R2, at the temperature T2. We want to find out the temperature coefficient of resistivity. Again easy. Okay. You can have the formula that we know very well. Final resistance R2 is equal to initial resistance 1 plus alpha T2 minus T1, and put these values here. Just you have to put the values and you will get the value of alpha. Okay, the value of R2 is 2.7, value of R1 is 2.1, 1 plus alpha, then T2 minus T1 you can take 100 minus 27.5. Okay, and you can simplify this very easily. Okay, 2.7 is equal to 2.1 plus 2.1 alpha 100 minus 27.5. Okay, this 2.1 can be taken on the other side. It becomes 2.7 minus 2.1, so it becomes 0.6, and that is equal to alpha into 2.1 into 100 minus 27.5 is nothing but 72.5, and write there or make alpha as a subject of formula. You will get its value to be 0.00394. Okay, alpha you will get 0.00394 degrees Celsius inverse. So it is easy. Okay. Now we talk about the next numerical 3.8. A heating element using nichrome connected to 230 volt supply draws an initial current of 3.2 ampere. So try to understand. Initially the current is 3.2 ampere and the voltage is 230. So initially the resistance of that nichrome wire will be 230 divided by 3.2, and that value of resistance will be round about 71.875 ohm. So this is the initial value of resistance. Now this current settles down after a few seconds. Okay, it is getting settled. Okay, it is becoming steady, and at that time the current becomes 2.8. So try to understand. Now the current is different, so the value of resistance, that is say R2, that of the nichrome wire, because current is changing, the value of resistance will change. It becomes V upon I. Now the voltage is same, 230. Voltage is same, but the value of current is different. So 2.8 you have to take as the new current. So now the resistance becomes 82.143. So initial resistance was 71.875. Now this current has settled and new resistance has become this much. Okay. Now temperature coefficient of resistance of nichrome is given 1.7 into 10 raised to minus 4 degrees Celsius inverse. We want to calculate the new temperature of the nichrome element. Okay, we want to calculate as it is becoming hot, as the current passes through it for some time. What happens, its temperature gradually increases. Okay, so new temperature, we want to find out what is the steady temperature of the heating element if the room temperature is 27 degree Celsius. Okay, so now we want to calculate the new temperature. Okay, now the values of R2 and R1 we have calculated. So now you must write those values. Okay, and the formula which we are having, we have R2 is equal to R1 1 plus alpha T2 minus T1. Now you can do it very easily. R2 is given, or rather we have found it is 82.143 is equal to R1, we got 71.875 into 1 plus alpha is given to us 1.7 into 10 raised to minus 4. Okay, into bracket T2 we want to calculate, minus T1 is given, reference temperature is 27 degree Celsius. Okay, so now it's easy to calculate. You can write 82.143 divided by 71.875 is equal to 1 plus 1.7 into 10 raised to minus 4 T2 minus 27. Okay, so this value is round about 1.143. This 1 goes on the other side, so it becomes minus 1. Okay, is equal to 1.7 into 10 raised to minus 4 T2 minus 27. Okay, so now you will get 0.143 of this. Okay, so we can write 0.143 is equal to the value of coefficient of the temperature coefficient is 1.7 into 10 raised to minus 4 T2 minus 27. Now 0.143 upon 1.7 into 10 raised to minus 4 is equal to T2 minus 27. This you can simplify. Okay, and this 27 can be taken on the other side, it must be added. Okay, this much you can do. Okay, this becomes as such 1430 divided by 1.7 plus 27 is equal to T2, because this 10 raised to minus 4 goes up, so it becomes positive and multiplied with 0.143, so it becomes 1430 divided by 1.7 and plus 27, so the T2 finally you will get, that is 868.2 degree Celsius. So calculative part you can understand easily. Okay, now we talk about the numerical number 3.10. 3.9 we shall calculate afterwards, that separate video I will put. In a meter bridge, the balance point is found to be at 39.5 cm from the end A, when the resistor Y is 12.5 ohm. Determine the resistance of X. Y are the connections between resistors in Western bridge or meter bridge made of thick copper strips. That part we shall discuss. The other part is also there. Now, so I try to understand the meter bridge is having its figure. You must know the figure of meter bridge. Okay, this is the L-shaped strip. Okay, rather slightly down I will draw. Okay, this way the strips are. Okay, here there is another strip and this is the another strip, and here 1 meter long wire is kept. Now see, here we have joined one resistance whose value is X. Here we have joined another resistance whose value is Y. And this value of Y is given, how much it is? 12.5 ohm resistance. Okay. Now we have the galvanometer here. Okay, this is galvanometer and its free end is somewhere here, and we are getting the null point at L1 is equal to 39.5 centimeter. Okay, now we want to find out the value of X. Now see, the balance condition is like this: X upon Y is equal to L1 upon L2. So here Y is given, L1 is given, L2 can be found. L2 is 100 minus 39.5, the remaining portion. This remaining portion will be 39.5, you have to subtract from 100. So this remaining portion you will get, that is L2. So you can easily find the value of X. X is equal to Y. Y is 12.5 multiplied by 39.5, that is value of L1, divided by L2 is nothing but 100 minus L1. So 100 minus 39.5. So whatever value you get, multiply these two and divide by this value, you will get the answer to be X. Answer of X to be 8.16 ohm. Okay, this will be the answer of X. Okay. Now the question is, why do we use the thick metal strip? Thick metal strip which is there. See, these are the thick metal strip. Okay, these are the thick metal strip. Thick metal strips are having less value of resistance, so the resistance of these thick metal strips can be neglected in whole process. That is why we are using this thick metal strips. Okay. Now the other part, determine the balance point of the bridge given above if X and Y are interchanged. Now you are interchanging the X and Y. So X goes at this position and Y comes at this position. Okay. So the whole picture is different now. Okay. This will be the new position. Okay. Here we have Y. Okay, Y is at this point and this X comes at this section, in this section, and this is the galvanometer and all. That is okay. Now we want to find out the balance point. So L1 we want to find out, say for example. Okay, so Y upon X, now it becomes Y upon X is equal to, say, L1 prime. This is, say, L1 prime because newly arranged condition, and this becomes 100 minus L1 prime. Now Y is with us. Y is 12.5 upon X we got 8.16. Okay, and L1 prime upon 100 minus L1 prime. Now just you cross multiply this and make L1 prime as the subject of formula. You will have the value of L1 prime to be round about 60.5 centimeter. Very easy calculation, cross multiplication, and then make L1 prime as a subject of formula. Okay. Now 3.11, storage battery of 8 volt and internal resistance 0.5 ohm is being charged by 120 volt battery. That is, DC supply is charging the small battery of 8 volt whose internal resistance is 0.5 ohm. Using the series resistors 15.5 ohm, that is kept to control the current in the circuit. What is the terminal voltage of the battery during charging? What is the purpose of having this series resistor in the charging circuit? Now see, I am drawing the circuit first of all for you. Okay. Now here we have a small battery of 8 volt first of all. 8 volt battery is charged. Okay, it is having internal resistance. Internal resistance is how much? 0.5 ohm. We say this is R. Then another resistance to control the current is kept, external resistance R, whose value is given to us 15.5 ohm. Okay, now here another battery, big battery to charge, okay, whose value is 120 volt. Charging is done when positive is connected to positive, negative is connected to negative. So this is charging condition. Okay. Now see, current will always flow from higher voltage battery. It goes like this, charge the battery, okay, and this way it happens. Now this is the direction of current. We do not know the value of current. Let current in the circuit is I. Now we are applying the Kirchhoff rule in the anti-clockwise direction. In which direction? Anti-clockwise. Okay, so this direction is the direction of motion for me. I begin from this 120 volt battery. I am going from negative terminal to positive terminal. In this direction I am moving. So when I move from minus to plus on the terminal on which I am reaching, that sign I have to take. So plus, I write plus 120. Then from plus to minus I am moving in this small battery of 8 volt. Okay, in this 8 volt battery I am moving from plus to minus. This is positive terminal and this is negative terminal. Okay, so plus to minus, if I am moving, then I have to write minus 8. Then with the current I am moving, see, in the direction of current I am moving, so minus I have to write minus I, that is the value of current, multiply by the resistance through which I am moving, that is I into R. Again, here you can see this point, okay, capital R, I am moving with the current, so minus I into R, and that is equal to 0. This is the way I can apply the Kirchhoff's rule. Now 120 minus 8 is easy, 112. On the other side you can take these two terms, okay, I can be taken common, it becomes R plus R. Now you can find easily the value of I, isn't it? I can be found, okay, I is equal to 120 minus 8 is nothing but 112 upon R plus R. 112 upon capital R is 15.5, the small r is 0.5, so it becomes 16. So this becomes 7 ampere current. So it's very easy to calculate what is the current. First of all we found, okay. Now we want to find out the terminal voltage of the battery during charging. Now see, whenever there is a process of charging, the voltage drop. See, whenever discharging process is there, try to understand. At that time, terminal voltage is E minus IR. Now, whenever there is a charging process, then that much potential drop will be added in this. This resistance as such R is not outside, it is inside the battery. It is internal resistance. Just to simply show it, we show it outside. Otherwise this resistance is inside, so this value becomes positive, or that much potential will be added, okay. So whenever there is a charging process, the potential drop or other terminal voltage across this voltage, this small battery, the terminal voltage can be found by writing E plus IR. If it is discharging, then it is minus. So here it is very easy. E is, that is electromotive force of this battery, is 8 volt plus the current which you got. How much current did you get? 7 into the value of the internal resistance, that is 0.5. Okay, so 8 plus 3.5, and this becomes 11.5 volt. Okay, so 11.5 volt will be the terminal voltage during this process. Okay, now numerical number 3.12. In a potentiometer arrangement, a cell of electromotive force 1.25 volt. The cell is having 1.25 volt. Okay, EMF gives the balance point 35. Okay, if the cell is replaced by another, then it gives the null point as 63. What is the EMF of the second cell? Very easy. E1 upon E2 is equal to L1 upon L2. Just put the values of L1, L2. E1 we are having, we want to calculate E2. Okay, so E2 can be made as a subject of the formula. Okay, E2, or rather we can write again E1 upon E2 is equal to L1 upon L2. So we can write it again as E2 is equal to E1 into L2 upon L1. Okay, this way you can make E2 as a subject of formula, because we have E1 upon E2 is equal to L1 upon L2. So E2 can be written in this way, E1 L2 upon L1. Now E1 we are having 1.25, L2 we are having 63, and L1 we are having 35. So easy calculation, 2.25 volt you will get. Okay. Now 13th one, the number density of free electrons in the copper conductor is given. Okay, estimate in example 3.1 is 8.5. This is number density. How long does an electron take to drift from one end of the wire, that is of 3 meter long, to the other end? Okay, cross sectional area is given, current is given 3 ampere, so I is equal to 3 ampere. This is the area of cross section. Okay, this is 8.5, that is 8.5 10 raised to 28 is the number density, that is number of electrons per unit volume. Okay, so this much is given. Now easily you can calculate this. Okay, because I is equal to AVDNE. This is a very simple formula that we are using. Okay, current I is equal to AVDNE. Okay, now see, this is the length of wire. So drift velocity is length of wire, distance travel upon time taken. So easily now you can replace this Vd by L upon T. So I will be equal to A L N E upon T. So now you can say this is your wire, length is the L. Okay, so you can easily now find the time. Okay, time is equal to A L N E upon I, and all these value, cross sectional area, length of wire, N is given, E is known to you. What is E? E is charge. Charge is how much? E is 1.6 into 10 raised to minus 19 coulomb. That you must know. Okay, 10 raised to minus 19 coulomb, that is charge of electron which is moving, and I is also given. So you can easily find the value of the time, and that you will get 27200 second. Okay, so this is very easy calculation, do it. Okay, calculate all this numerical 3-4 times and practice. Thank you.